Hi, from now on I'm going to present the work submitted to COBEM 2021, titled Spectral Kurtosis based on the Supervised Learning Method for Estimating Remaining Useful Life of Rotating Machinery. It's a research developed by Leonardo Godói, a PhD student, and Eurípedes Nóbrega, a professor at the University of Campinas in Brazil. Predictive maintenance consists of predicting the potential occurrence of failures before they reach critical levels. Therefore, the predictive paradigm is more complex than the corrective and the preventive ones. In a condition monitoring system, it's common to perform three different tasks: diagnostics, to identify the machine or component health state; anomaly detection, to indicate the occurrence of abnormal behaviors over time; and prognostics, which is the prediction of failures itself. The prognostics includes the main challenges that currently exist in this area. The biggest one, which will be addressed here, is the estimation of the remaining useful life, the RUL, which aims to determine how long a machine, in terms of some of its critical components, is capable of operating before it fails. The methods for estimating the RUL can be model-based or data-driven. Model-based methods use mathematical models described based on physical aspects to represent the system and its failure mechanisms. Data-driven methods, in addition to not requiring complex modeling and deep knowledge of the system, have proven to be very efficient and robust. Our method uses spectral kurtosis for extracting frequency domain features and an autoencoder neural network to produce a health indicator based on its reconstruction error. As a statistical feature, the kurtosis indicates the dispersion of the values of a set in relation to its central tendency. Spectral kurtosis has received much attention in the recent years as a way to measure the kurtosis of the frequency components of a signal, proving to be really useful for the characterization of non-stationary signals. To preprocess the health vibration data that compose our model, we used an unbiased estimator of the spectral kurtosis, which is computed based on the fourth order and the second order cumulant of a frequency bin. The kurtogram is a way to represent the spectral kurtosis along the frequency and the frequency resolution plane. Intuitively, the kurtogram can be seen as an image. In our method, each segment of vibration samples is converted into a kurtogram image, containing their respective frequency domain characteristics at different resolution levels. This is the main advantage of the multi-resolution analysis. While methods such as the principal component analysis perform only linear transformations, autoencoder networks are capable of modeling complex nonlinear functions. An autoencoder is formed by the encoder, the part on the left, which reduces the dimensionality of the data, and the decoder, on the right, which restores the original dimensionality. After training, the decoder is discarded and the model is described only by the encoder and the average of the encoded vectors generated at the encoder's output. Here, each kurtogram is flattened before feeding the network, so that its image element is treated as an input neuron. Finally, the autoencoder generates in the output layer a vector of image elements that tend to be as close as possible to those provided in the input. The method we proposed for estimating the RUL of a rotating machine is summarized in this diagram. In the modeling phase, the health RUL vibration signals of the monitored component are preprocessed, transformed into kurtogram images. The set of flattened kurtograms is then processed by the autoencoder network, which is trained to learn how to reconstruct health data. In the test phase, the older data undergo the same preprocessing procedures and are processed by the autoencoder trained in the modeling phase. The representations encoded in the test are compared with the health data encoded vector, and the difference given by the root mean square error results in the reconstruction error, which is used here as an indicator of the component's health. So the greater the error, the more difficult the network has to interpret the signals, and consequently the greater the degradation. To validate the proposed model, we used the data provided by the Fento-ST Institute from France, obtained through the Pronostia bearing test platform. This platform was built to simulate bearing failures. For this purpose, there's a mechanism that forces the wear of the bearing, allowing degradation processes that would normally take days or months to be observed in just a few hours. We can see here two plots. On the left, the roll vibration in the x direction of the chosen run-to-failure series, denoted by A. On the right, the corresponding indicators produced by the RUL method. Only the first 25% of the data were used for training the network. With this, we can also define as a threshold the highest value of the indicator's moving average, which in this case was 0.28, indicated by the red line. This same threshold will then be used as a reference for predicting failures in the next experiments. This plot contains the results obtained with the first test set, performed with the subset denoted by B. Here we can visualize two regressions. In purple, the long-term regression, and in blue, a compound regression composed of consecutive local regressions. In this case, we can observe that the short-term regression, the blue one, is the most pessimistic as it reached the threshold first. So from there, the resulting RUL was 68 minutes, 27 less than the actual RUL. So the error is approximately 28%, a relatively satisfactory number when it comes to a RUL task. In the second test subset, here referred to as a subset C, the threshold is also first reached by the short-term regression. In this case, the difference to the actual RUL was just 1 minute, because the expected was 6 and the predicted was 5, resulting in a relative error of approximately 16%. In the third test, performed with the subset D, unlike the previous tests, the long-term regression, the purple one, was the first to reach the threshold. In this case, for the actual RUL of 126 minutes, we got the estimated RUL of 190 minutes, resulting in a relative error of just 13.49%. We listed here the main results observed from the tests performed. The estimation of RUL is an extremely difficult task, and comparing the relative errors obtained by our method with those obtained in other similar works, which commonly exceed 30 or 40%, we can say that the results of our method are satisfactory. In all tested cases, the pessimistic RUL, that is, lower than the actual RUL, provides more safety in practical applications, as it ensures that the machine's operation will be interrupted before the failure propagation. Finally, it can be concluded that the Spectral Kurtosis is a tool capable of efficiently extracting features and consequently indicating current degradation patterns in the data. We would like to thank the financial support of São Paulo Research Foundation, FAPESP, the Fento-ST Institute for making the data publicly available, and the COBEM for enabling the dissemination of our research. Thank you so much for watching.